It's Monday morning at North Star Retail. Analyst Sarah Chen has just been handed 2 years of daily sales data and a Friday deadline. Her assignment: build a 90-day forecast predicting next quarter's revenue. If she were building a standard machine learning model, Sarah could treat every row in that spreadsheet as an independent event. Standard algorithms assume data points don't care about their order, meaning you can shuffle them like a deck of cards to train the system. Time series data upends that logic. Today's revenue is tied to whatever happened yesterday, the same day last week, and the equivalent week last year. If you randomly shuffle chronological data to train your algorithm, you scramble that chain of cause and effect. You destroy the sequence required to predict the future. Because time enforces a specific order, Sarah must set aside standard modeling and adopt a toolkit designed specifically for chronological data. By Tuesday, the real work begins. Before Sarah can think about predicting the next 90 days, she has to isolate exactly what drove the past 2 years of sales. STL decomposition strips raw sales data into core layers. It extracts the long-term trajectory, called trend. It isolates repeating rhythms as seasonality. The remaining mathematical noise drops as the residual layer. A repeating bump here means a missed seasonal cycle. Forcing the data through this breakdown ensures the eventual forecasting model learns actual business drivers rather than accidentally memorizing random market noise. On Wednesday, the sheer complexity of the data often tempts analysts to reach for the most advanced algorithms first. Professional forecasters resist that impulse. Instead, they start with the simplest possible math. A naive model predicts by copying yesterday's exact number. A seasonal naive model reaches back and copies the exact number from 1 year ago today. From there, analysts step up to exponential smoothing, or ETS. This classical model adjusts for trend and seasonality using a few intuitive mathematical weights, and it serves as the minimum standard for performance. These simple mathematical models provide the bar that every other model must clear. If a complex machine learning model cannot outperform a basic ETS forecast, the complex model is discarded. By Thursday, Sarah realizes North Star's data contains multiple overlapping sales rhythms. To capture weekly cycles sitting on top of annual cycles, she needs a more robust model called gradient boosting. However, gradient boosting algorithms are blind to the passage of time. They do not naturally understand the difference between a Monday and a Thursday. To fix this, Sarah creates lag features. She builds new columns into the data that tell the algorithm the sales values from 1 day ago, 7 days ago, and 365 days ago. By converting history into static columns, she translates the abstract march of time into a tabular math problem the model already knows how to solve. Friday morning arrives. Sarah has a working forecast, but before presenting it, she must mathematically prove it will perform in the real world. Standard K-fold pulls random segments to test. On time series, this creates a paradox. Training on tomorrow to predict yesterday produces fraudulent scores. The solution is time series split, enforcing chronological discipline to train only on past data for the adjacent future. When Sarah presents her 90-day forecast on Friday afternoon, she doesn't offer a single guaranteed number. She provides a widening range of possibilities, mapping how uncertainty grows the further out she looks. Predictive power isn't achieved by throwing massive algorithms at a wall of data. It comes from rigorously preventing the future from leaking into the past and honestly embracing uncertainty.